All right, we are going to switch gears a little bit, and we are going to move from discussing collisions and conservation of energy and momentum, and we're going to now talk about rotation. And so up until this point, pretty much everything we've done is focused on linear or translational motion. We did talk about uniform circular motion at one point, but now we're going to switch gears and we're going to focus for a little bit on this idea of rotation and objects that maybe are better described using a slightly different notation or formalism because the objects are traveling in an orbit or rotating rather than in a linear fashion. And so the first thing we want to do is we want to revisit an object moving in a circle. So I've got an object here that's moving along this path. And so you can see the circle here, so that the object here is orbiting counterclockwise. And if you want, you could describe the position of the object with an x variable and a y variable. But you can also use different variables. And so what you could also do is you could take into account the angle here, this angle theta. So wherever your particle is, that would correspond to a different angle. You could also specify how far you are from the origin, from the center of the circle. And then S here, that would correspond to the path length, so the curve path out there on the circle itself. And so we are going to start to think about those quantities as opposed to our x and y and z variables. So first thing to notice is that the variable theta, the angle here, is related to the radius of the circle and the arc length. And so this relationship right here, theta equals s over r, and then you can rearrange that and just say that s is equal to r times theta. Now, what we need to do is revisit the cross product discussion that's in the video from chapter 2. So make sure you go back and take a look at that, look at the notes, because even though the magnitude here of s is r theta, if we want to talk about the vector quantity s, then what we need to do is think about the cross product of theta and r. And so one thing about cross products is that the vector theta and r, the resulting vector s, is perpendicular to both theta and r. And so in my picture down here, I've got my traditional XYZ coordinate system, and then I've got a visualization for what you can think of for the directions of our theta vector, the r vector, and the s vector. And so this is a 2D picture, so you can think of the x and y plane here, where my circle was. So r points out towards the location of the object, right, that position vector. So from the center out, and that vector, right, could swing out anywhere in the xy plane. We just happen to have it drawn right there. S is pointing perpendicular to the direction that the object is moving. So that's 90 degrees right there. And then outside of the xy plane, so in the z direction, that is the theta vector. So that's our definitions. And then what we want to think about the motion of an object that's that's traveling around in the circle. So what happens if theta changes? And so this is going to introduce angular velocity. So our definition for angular velocity is, how does theta change with time? So take the derivative of your theta function, take that derivative with respect to time, that gives you the angular velocity. And one thing that we want to point out, so this is omega, the units for angular velocity are radians per second. And to put that into context, one revolution around the circle would be 2 pi radian. It'd also be 360 degrees. So you may see angular velocities or angular speeds reported as revolutions per minute or degrees per second or degrees per hour. Ultimately, though, if we're going to be using these quantities, eventually we'll probably want to get back into the unit radian, right? And so this is how you go from one to the other. Now, remember, since S is related to the product of r and theta, then that means our velocity, so s being the path length vector corresponding to the object moving on the circle, our translational speed, just like this is our sort of linear position quantity, our translational speed is omega times r. So just take the derivative of both sides with respect to t, and we end up getting v on this side and omega on this side. So the speed is related to the angular speed by a factor of the radius over which the circular motion is happening. And then this is also a vector quantity, so again, we need to be thinking about the cross product. Omega, the cross product with the r vector, gives you the translational velocity vector. And so you can see this picture here again, same idea, I've just swapped out velocities rather than positions. Again, the velocity, the angular velocity, and the that position vector, those are all, the radial position vector, those are all perpendicular. Now, of course, next up we have angular acceleration. And so the angular acceleration symbol is alpha, and we get the acceleration vector much in the same way as with our translational quantities by taking the derivative with respect, the time derivative of the velocity, and so the omega quantity, angular velocity, which also corresponds to the second derivative, right? The second time derivative of the theta vector. So angular acceleration, the typical unit you'll see is radian per second squared. Note, since our translational velocity is omega r, then that means the translational acceleration is alpha r. And again, a cross product is if you want to talk about the vector, so the translational acceleration is the cross product between the angular acceleration and this r vector corresponding to the radius of the circle. So one thing that is incredibly important to appreciate and realize and makes investigating rotational motion or angular motion so natural as we transition from translational motion is that all of our linear expressions or our translational expressions for motion, so here I have my kinematic equations listed, all of those have an analog in rotational or angular motion. And so all we need to do is make the transition from x to theta, v to omega, a to alpha, and then we get these three kinematic equations that now describe objects that are undergoing angular motion or rotational motion. And so analyzing the rotational motion, it might take a couple practice problems for us to get comfortable with the idea, but the equations are exactly the same format. The way we use them is exactly the same. We just need to get in the habit of recognizing when it's appropriate to be using these rotational equivalent expressions as compared to our linear or our translational equations.